In this lecture, we're going to talk about the naive-Bayes classifier as an example also of generative classifiers. And I will also talk about some other details like comparing the performance of different classifiers and some aspects of data preprocessing that so far we have not been looking at in great detail, but just to point out some problems, some issues that may occur. So I'm going to start a bit with a revision of probabilities, Bayes rules, and then move on to the Bayes classifier and explain the need for this simplification that will result in the naive-Bayes classifier. And then we'll see how we can compare classifiers and some details about preprocessing data. So let's start with some basic notions of probability. Let's assume that we have these two random variables, x and y. They can have these values. For example, x can have values 1, 2, 3, 4, y can have 2, 3, 4, 5, 6. And so we have probabilities of combinations of values. This would be the joint probability distribution of the two variables, which gives us the probability of having x equal 2 and y equals 3, for example, in this place here, and the probability of x3 and y3, and so on. Now we can compute the marginal probability of one of these variables having a given value, for example, the marginal probability of x being 1, by summing the joint probabilities of all the occurrences here where x is 1. So we are going to do this sum over all possible values of y and add the joint probability of x being 1 and y being each of those values. So we are summing, for example, this column, and this gives us the probability of x being 1 regardless of what y is. So this is why we call it the marginal probability, because we find it here at the margins if we do this sum on the table with the joint probabilities. Okay, another thing that we can ask is what is the probability of y having some value if we know the value of x. That is, this is the conditional probability. So let's say we know that x is 1. What is the probability of y being 4? We know that the probability of y being 4 and x being 1 is 0.035, but this is for the overall distribution of probabilities. If we know from the start that x is 1, we are restricting ourselves to this column here. So actually the probability of y being 4 is this 0.035 in proportional to the sum of values in this column. That is to the probability of x being 1. So this is the conditional probability. The relation between the conditional probability and the joint probability is that the conditional probability of y having this particular value, given that x was fixed on this value, so this is something we assume from the start, is the probability of, by chance, both of them having those values divided by the probability of x having that value. So this is an important relation because it allows us to compute the probability of one of the variables having some value after we fixed the value of the other from the joint probability distribution, or vice versa, because then we can change this and compute the joint probability from the conditional probability and the marginal probability. So to summarize, we can compute the probability of one of these variables having a given value by adding the joint probabilities over all the values of the other variable. And we can relate the joint probability of these variables, that is the probability that they fall into these particular values, relate this to the conditional probability, which is the probability of one of them having some value given from the start that we already fixed the value of the other. And so we have a relation between these two by multiplying by the marginal probability or dividing if it's on the other side of the equation. Okay, so since we know that the probability of y having some value and x having some other value is the same thing as x having that value and y its value, because it doesn't matter the order we consider the variables here, we can apply this product rule and use this equality here. That is the probability, the conditional probability of y given x multiplied by x would be the same as the conditional probability of x given y multiplied by the marginal probability of y. So if we rearrange this, we obtain Bayes rules, which is this expression here at the bottom, which relates the conditional probability of one variable given the other to the conditional probability in reverse, and then the ratio of the marginal probabilities. So what can we do with this? If we take a frequentist interpretation of probabilities, then probability is merely the frequency of some random event over infinite trials. So if we repeat the experiment infinite times, the frequency with which something occurs is equal to the probability of occurring. So under this interpretation, Bayes' rule simply relates this different perspective of computing the relation between these frequencies. So we are just looking at the frequencies over infinite trials of y having some value within the subset of cases where x had that particular value, and relate that to the reverse, the frequency of x having that value within the subset of cases where y has that value. So this would be just changing the perspective on the variables. But a Bayesian interpretation of probabilities is fundamentally different. In this case, we are interpreting probability not as a frequency of random events over infinite trials, but as some sort of rational measure of how certain we can be about the truth of some hypothesis. So it's not about the actual events being random. They may not be random. It's about our confidence or our certainty on those hypotheses. And in this interpretation, we can see these Bayes rules as allowing us to revise our confidence in some hypothesis based on the evidence we acquire. So the idea here is that the conditional probability of some hypothesis given some evidence, and in this sense, Bayesian sense, the probability will be our confidence that the hypothesis is true, would be a function of the prior probability the hypothesis is true. That is something we assumed about how likely the hypothesis is to be true. The probability of the evidence being observed if the hypothesis is true. So something, does the hypothesis predict that we're going to observe this evidence, and how surprising a priori this evidence is. So the marginal probability of the evidence gives us an idea of how we were confident this evidence would appear regardless of the hypothesis. So one example of this is when Einstein proposed that gravity was actually a distortion in space-time. An implication of that would be that the sun's gravity would distort the trajectory of light from distant stars. And so an observation was made during a solar eclipse to check the apparent positions of stars close to the sun during the eclipse. And this was in accordance to what Einstein predicted. So here we would find evidence that was very surprising. Nobody was expecting the light from the stars to be twisted, the trajectory by the gravity of the sun. But this was implied by the hypothesis, by relativity. And so this resulted in a large boost in the confidence on the truth of that hypothesis. So this, if we interpret this in this way, we can look at Bayes' rules as a way to compute the confidence we have that an example will belong to some class given the features that the example has. And we can compute this from the joint distribution of from the conditional probabilities of the example and the class, and the marginal probabilities of the example and the class. Under a frequentist interpretation, this would be a bit strange, because it would imply that the example belonging to a class was a random variable, had some probabilities. And this may not be a good way of thinking about classification problems and so on. But under the Bayesian interpretation, we are measuring here the confidence that we have on the assignment of the example to that class. So we can use estimates from the data to obtain these values, and this gives us an idea to which class we should assign each example. So this brings us to Bayes classifier. We can, in the Bayesian sense, consider that there is a probability of an example with some features. So given the features that we have, a probability of belonging to each of the classes. This makes more sense in the Bayesian interpretation, because the probability here means our confidence that the example belongs to that class. It does not imply that we are assuming that examples belonging to classes are random events. They may not be. The example either belongs to that class or it doesn't, but it's not a random variable. So under this interpretation, we can consider that the probability, this marginal probability of the example having some features will not be dependent on the class, because this is just the overall probability of having those features regardless of the class. And since we want to find not the exact value of this conditional probability, but we want to choose the class for which this conditional probability is highest, we can ignore this part here, the marginal probability of X, and just consider that the conditional probability of belonging to this class, given the features of the example, is proportional to some prior probability of belonging to that class multiplied by the conditional probability of having those features if it belongs to the class. And now we can check this and find for which class we have the highest value here. Now this product here, the prior probability of the class multiplied by the conditional probability of the features given the class, is the same as the joint probability of the class and the features. So these are equivalent. So basically all we need to do for the Bayes classifier is to find the joint probability distribution of classes and features, and then for each combination of features we pick the class that has the highest value. So this would be very simply the Bayes classifier. The class where we are going to assign this point with features x, so this is a vector with all the features of that example, will be the class C for which the joint probability of belonging to C and having all those features is the maximum. And this is an ideal classifier in the sense that it minimizes the error. So if you always assign each point to the class where the probability of that class occurring with those features is highest, you minimize the error you're going to commit on your classifier. Now, this would be a very good thing, because we would have an ideal classifier. We could minimize the error in all situations. The problem is, how do we find this class in practice? Because we need the joint distribution of classes and all the combinations of features. And this is the big problem with the Bayes classifier. Let's consider a hypothetical example. Suppose we have subjects, some with diabetes, some are healthy, and we are trying to find a way to predict diabetes from questions about feeding habits of food, what kind of food they eat, what exercise they do, professions, and so on. So suppose that we have 20 questions. Each one can be answered with yes or no. And now we're going to use the answers to those questions to try to predict if a person will have diabetes or not. So if we have 20 questions, we have, even with only yes or no answers, we have around 1 million combinations. That's 2 raised to the power of 20. If we want to estimate the probability of each class, diabetes or healthy, for each of these 1 million combinations, we are going to need many millions of questionnaires, because we need to find several examples for each combination of X, so that we can we can estimate the probability of being diabetic or healthy. And also, when we start gathering this data, we are going to have some kind of combinations that are more frequent and some that are rarer. So we'll need many millions of subjects in order to be able to create a Bayes classifier when we look at the joint probability distribution. So in general, the Bayes classifier is not something we can use in practice. We never have enough data to compute the joint probability distribution of the classes and all combinations of features. So even in this very simplified example, it would not be practical. If you have more complex examples, then this will seldom happen that you can use Bayes classifier. So what we need here is to do a simplification, and this is what leads us to the naive Bayes classifier. Let us assume that if we fix the class, if the class is already given, then all the features become independent. This is called conditional independence. It's not the same as being independent. For example, if you have two people that live on the same street, the time they arrive home may not be independent, because it may be subject to traffic conditions, to strikes on the subway or something like that, and this can affect both of them, so the time they arrive are correlated. But if you fix those other conditions, for example, if you know that the subway is stopped due to a strike, then the time they arrive will no longer be correlated under those conditions, because the effect is the same for those, and what is left are other things that are affecting them independently. So this is the idea of conditional independence. The variables are not independent, but if you fix some other conditions, some other thing, then they become independent. And this is what we will assume in the naive Bayes classifier. Note that this may not be true in the data. We are just assuming that so we can simplify the estimates of the joint probability distribution. So let's consider that we are computing the joint probability distribution of the class, and that features vector x, which I'm going to decompose here in all the different features, feature 1, feature 2, etc., and feature n. We could apply the product rule here and say that this is the probability of having this class, being in this class, multiplied by the probability of feature 1 given the class, then the probability of feature 2 given the class and feature 1, and so on for all the features. Now this is the problem that we have, because now we have to find the probabilities of all these combinations, and we don't have data for all of that. But if we assume that once we know the class, the features become independent from each other, then everything that has the probability of one feature given the class and other features becomes the same as the probability of that feature given the class, because once we give the class, everything else we assume to be independent from the first one, or from each other, and so it does not affect the probabilities there. So this greatly simplifies the expression here. And so we can consider that the joint probability distribution of the class and all the features is simply the product of the prior probability of the class. This is a priori what is the probability of any point at random falling on each class, multiplied by this product, which is the probability of each of the feature values that the example has given that class. If we take the logarithm, we can convert this into the sum of these logarithms. And so the naive Bayes classifier, we can write it like this. We are going to classify an example x into the class that maximizes this sum, the logarithm of the prior probability of the class, plus the sum of the logarithm of the probability of each feature value this example has, if the example belongs to that class. So why is this? Does this become simpler? Because now we just need for each class to find the probability distribution of the features. And also for each class, we can find the prior probability of a point belonging to that class. And now we just compute this for each point to classify and choose the class with the largest one. Let's see what this means for the diabetes example. If we have these questionnaires, we can ask our subjects for the training set to fill in the questionnaires, and we're going to split them into two sets, the healthy subjects and the diabetic subjects. And now, for each of these two sets, we count the fraction of yes, no for each question. So we know the probability of answering yes on each question if the subject is healthy, and the probability of answering yes on each question if the subject has diabetes. And note that for this we only need a few tens of examples, and we already have a good idea because we split into the two parts, and if we have, for example, 10 or 20 answers to a question, we can have a good estimate of how probable it is that they answer yes or no. And now we use the prior probability of belonging to this class. The logarithm of that is simply the logarithm of the fraction of healthy individuals in the population or diabetic individuals in this group. And we add the logarithms of all of these different probabilities that we computed here for the different classes. So let's see some examples to illustrate this better. Let's suppose we have this data set here. We have two continuous features. We have x1 here and x2 here, and the two classes, the red and the blue classes. And we want to create a naive Bayes classifier to help us predict the class of a point given these two coordinates, which are the features of the examples. Now, one way to find distributions with continuous values, such as this example, would be to use a parametric method. That is, we have a distribution with some parameters, for example, a normal distribution, and now we compute the parameters. In this case, for a normal distribution, we need the mean and standard deviation. So if we computed the mean and standard deviation of each of these coordinates on each of these classes, we would have the parameters for the naive Bayes classifier. And this, by the way, is how you have it implemented in scikit-learn. You can use a naive Bayes classifier specifying the probability distribution, and so it computes the parameters and has this approach. We can also create a non-parametric naive Bayes classifier if we do not assume the distribution with some model that has some parameters. For example, we can use kernel density estimation, which just stores the data and then computes the value, the probability density at each point from the data by adding those kernel functions. So basically, these two approaches are that in a parametric model, everything is completely defined by the parameters. So once you train everything, you can throw away the data. You don't care about it anymore, and everything is determined by the parameters you found. With the non-parametric method, you need additional data. You don't have parameters that define everything. You may have some parameters, for example, the bandwidth that we use in kernel density estimation or something like that, or the k-value in k-nearest neighbors, but you still need the data because the parameters do not define everything. With a naive Bayes classifier, you can have either a parametric or non-parametric model depending on how you compute those probability distributions. If you use a parametric method to compute the distributions, you can just store all of these parameters in your classifier. This is a parametric model. If you don't, if you use, for example, kernel density estimation, then you need to keep the data and you don't have everything defined by the parameters. So let's do this with kernel density estimation. Just to recall from last week, what we are doing here is if we have a set of values, we can compute the density of this distribution by adding a kernel function centered on each of these values, and we'll have the kernel density estimation, this black line here. This differs from, for example, using a parametric distribution. This would be the example of considering a normal distribution on this data. This would be the mean and the standard deviation, but note that the data that we have here is not normally distributed. So this estimate here would not be very good for this particular data. We can also use things like histograms, and these are practical, especially if we have discrete values for our features. But with continuous features, if you want a non-parametric method, probably kernel density estimation is better, because it gives you a smoother result and does not assume something about the distribution of the data. So let's do this for each feature in each class in this example. So let's consider the feature that we have here, the horizontal coordinates. We're going to separate our data into the two classes. We have the blue points, and we compute the density distribution of these values for the blue points. This would be this blue line here. Note that there are more values around this range on the blue set than on this range here, and there is nothing on this part. So if we compute the kernel density estimation of the distribution, we have this blue curve here. We do the same for the red class, and now we have the distribution for the red class. So these lines give us the distribution of the values for this feature in the two different classes, in the blue class and in the red class. And now we can do the same thing for the other feature, which is the vertical coordinate here. And we have again the distribution of this feature for the red class and for the blue class. And now, since we are assuming conditional independence, then we can assume that the joint probability of these distributions, these features in the red class, is simply the product of the distribution of feature 1 and feature 2. We don't have to worry about all the combinations. We just multiply these conditional probabilities. Note that this is an assumption in our model. It's not necessarily true in the data. So it's not true that if we choose the red set of points, the features become independent. In this data, it doesn't appear to be the case. But we are assuming this in our model as a way of simplifying the computation of the joint probability distribution of the features in the red class. And so we have this surface here that gives us our estimate of the joint probability distribution of the features for the red class. And now we do the same for the blue class, and we can check for each pair of coordinates in this plane. We can immediately check which one is largest. If it is the probability of having those coordinates if it's in the blue class, or the probability if it's in the red class. So this way we can create a classifier. Now, one thing we may need to do, since we are using kernel density estimation, is to adjust the width of the kernel. Here, to simplify, I'm assuming that the width is the same for all the features. And if we use a very narrow kernel, we are going to have a more intricate, a more jagged line in this distribution. So the frontier where the blue becomes larger than red, or vice versa, becomes a lot more cut here with a lot more curves. If we use a larger kernel, then things become smoother. How do we optimize the kernel width? Well, we can use cross-validation. This is the example of tenfold cross-validation. This is the error in the training set, and this is the average for the validation in the cross-validation. And now we can find the best value for the kernel width. And this would be now the final result, training our naive Bayes classifier with the whole training set. So the idea here is that since we are assuming conditional independence of the features, we can just pick the red points, find the distribution of the probability of each feature for the red, the distribution of each feature for the blue points, and then the product of these probabilities, or the sum of the logarithm, because for numerical reasons it's better to use the sum of the logarithm so you don't get numeric underflows and problems like that. This would be enough to give us the class we want to predict to classify each point. So let's see another example with discrete values. This is a database of characteristics of mushrooms, and we have the mushrooms classified in two categories, poisonous and edible. And then we have features for the cap shape, the cap surface, the color, and so forth. And these features have these codes. For example, if the shape is the cap is bell-shaped, we have a B. If it's a conical, it's conical shaped, we have C, and so forth. So what we have is, for each mushroom, we have the classification, poisonous or edible, and then we have the features for all of these aspects of the mushroom: the cap, the surface, the color, the odor, and so forth. Now, for real applications, if you want, you can use some implementations in naive Bayes, naive Bayes in the scikit library. For the assignment, which I'm going to talk in more detail next week, you will implement your own naive Bayes classifier. So this is just to check, to make sure you understand the algorithm, and to give you an example of one of these classifiers from scratch that you implement. For the assignment, you'll have continuous features, so you're going to use kernel density estimation. In this example, since we have categorical features, we are just going to compute the frequencies, the fractions of the occurrence of each feature value in each feature. So something like a histogram where we have the different bars with the fractions. Okay, so first we are going to read all of these different letters for the features, and we are also going to add a question mark here because in some cases when you look at the data, there are some unknown features. So sometimes a question mark appears here, but we'll just add that as another possible value. So unknown is also a possible value for the features that we're going to use. There are many different ways of dealing with missing values, and this depends a lot on the actual problem you're trying to solve. So we're not going to worry about this. We're just going to ignore mostly this problem and consider that unknown is just another possible value on these features. In some cases, this may not be the more correct approach, but those are details that will depend on the actual application, so we're not going to focus on that. So this consists in just reading the file which describes all the features, splitting here on the equals sign so that we get these different letters, and we concatenate everything into a string. So for cap shape, for example, we will have this string, which is unknown, B for bell, C for conical, and so on. Then for the other feature, these possible values, these, and we have a list with the possible values for all the different features. Now we can read the data here. So we have the different values for the features, and we can store the indexes of these values. So the idea is that we're not going to store the letters, but this would be value 0, value 1, value 2, and so on. It makes it easier then to compute everything with NumPy. But this is basically parsing everything, computing the index on each of the string of the codes that we find here, so that we have numbers for all the different features, and then we gather that in the two tables, one which has the features and the other which has the classes. So basically we're going to separate this part here. We have the classes here, poisonous and edible. We are going also to assign them values 0 and 1, and we have all of these features which are letters here, but we are going to convert them into the index of each letter in these strings that we have here. So we convert everything into numbers, and we have everything into NumPy arrays. So I'm not going to go into much detail here on the code. This is just so if you want to experiment with this example and see how things work in detail and change the code and so on. But one important thing here is that once we have all of these both of these matrices, so the matrix with the features and with the classes, now we can shuffle everything. And it's important, if you separated the features from the classes, it's important that you do not shuffle them independently. Because if you shuffle the features and then you shuffle the classes in two independent steps, you will not have the correct class labels for the corresponding examples. So what one possibility here is to shuffle a set of indexes and then use the same set of indexes for the features and for the classes. So this would be one way of parsing the data and creating the matrix with the features and the classes. And now what we can do is to compute these frequencies of the value of each feature in each of the classes. Now, one problem here when you have actual data and you have these discrete values for the features is that it can happen that in your training data you do not have some specific value for some feature. For example, suppose that you don't have any mushrooms with bell shape cap on edible class in your training set. In that case, the probability would be 0. We would have problems with the logarithms, and the classifier would consider it impossible to have something with that value for that feature in that particular class, just because it never occurred in the training set. So to avoid that, we can use additive smoothing, which prevents these zeros from appearing. So in this basically consists in adding to the count of the value of some feature in this class one constant here, alpha, and then when we normalize by the frequency, we divide by the number of examples plus this constant multiplied by the different possible values on the feature that we are looking at. So if we use alpha equals 1, we are adding 1 to the count, and this is easy to do here by starting the count matrix all at 1. And then we increase for each position in the matrix as we find a particular value for each feature on that class. And then we just normalize by dividing by the number of examples plus this alpha multiplied by the number of features. So since alpha is 1, this is just the number of different feature values we have in that feature. Okay, so this allows us to compute the frequencies with which each value on each feature occurs in a given class. So we can now call this for the different classes. We are going to compute these, split the data into edible and poisonous, and then we're going to compute the different frequencies for the edible and for the poisonous. Note that in this case, I'm not going to do validation. I'm just splitting into train and test, both for the edible and the poisonous. And the reason for this is that in this particular example, there are no parameters to adjust. So since we don't need to adjust any parameters, we do not need to do validation. We are just going to train on the training set and then use the test set to have an estimate of what will be the error our classifier will commit when we apply it into future data points. You can do this by hand. I did it everything step by step so that it's easier to understand. If you want, in general, when you are going to split into training and test, you can use train test split from scikit-learn I just do everything step by step in these examples, at least in the first examples, so that you can experiment with them and really understand what's happening here. So now for classification, what we're going to do is to choose the classes according to the sum of the logarithm of the probabilities in for those feature values in the edible class, plus the prior probability of being edible, and the probability for the features having those particular values in the poisonous class, and the prior probability of being poisonous. Now, these prior probabilities here, we can compute them from the number of examples in each class. So we have a set of examples in the edible, here on the training set, in the edible class. We have another set of examples in the training set in the poisonous class, and we can see how much each of these sets is in proportional to the complete training set. So for example, suppose that 20% of the mushrooms are edible. In that case, our prior probability of being edible would only be 20%. We would start biased against being edible because 80% of the mushrooms would be poisonous. So this is important, that you have this prior probability computed from the proportion of the different classes, and then you add the logarithms of the probabilities of the features, and you check which one is largest. So if edible is largest, we retain the class 0. If not, if edible is smaller than for poisonous, then we change the class to 1, which is indicates that the mushroom is poisonous. So here is how we can bring everything together. We're going to split into training and testing for the training set, the edible examples, the training set for the poisonous examples, and then also for the test set, the edible and poisonous. Now we're going to compute the frequencies of all the feature values for the edible examples, and compute the frequencies of all the feature values for the poisonous examples. Note that we need to split these first into poisonous and edible, because we are assuming that these distributions are different in the edible class and in the poisonous class, and those are what we need to compute. We also need the logarithm of the probability of being edible and poisonous. So this is basically the number of examples in the edible training set divided by the total number of examples in the training set, and the same for the poisons. This gives us the fraction of edible mushrooms, the fraction of poisonous mushrooms, and the logarithm of that will be the logarithm of the prior probability. Now we can classify for the test set all the mushrooms that we have here, both the edible and the poisonous, and now we can compute the errors. So since we have edible mushrooms in the test set, these are errors if we classify them as 1, because edible is class 0. If we classify as 1 the edible, these are errors. The poisonous we consider to be class 1, so these are errors if we classify the poisonous mushrooms as 0, as edible, and so we sum these errors here. And now we can compute the confusion matrix and the percentage of errors and so on. So basically, our classifier on the test set just makes 191 errors. This is 4.7% error rate, and we have the confusion matrix here. Of course, this may seem very good, and in fact, when the mushrooms are edible, our classifier gets them right most of the time. It just discards 13 as poisonous, but there is a problem here. When the mushrooms are poisonous, there are 178 of them that our classifier is telling us we can eat them. So this is probably a worse problem than just the overall error rate. And this is something that we're going to see later on. The error itself, the error rate, may not be a good measure of how undesirable each error is, because some errors may be more costly than others. If we throw away an edible mushroom thinking it's poisonous, that's not very bad. But if we eat a poisonous mushroom thinking it's edible, that's probably very dangerous. Okay, so one thing that we have different in this kind of classifiers is that they are what we call generative classifiers. In discriminative classifiers, such as logistic regression, we are computing directly the conditional probability of the class given the features. This is actually what we are trying to approximate in logistic regression. So since we have at the end this conditional probability, we can compute the probability of belonging to a class if we know the features, but we cannot do the reverse. We don't know what is the distribution probability of the features if we know the class. For the naive-Bayes classifier, we are computing the joint probability distribution. We are simplifying that computation by assuming conditional independence, but it's still the joint probability distribution of class and the values for all the features. So this means that we have the probability distribution for the features. So we can generate synthetic examples given a class. We can do this in reverse. So consider this example. We use this training set. We compute the probability distributions for the two features for the two classes, for blue and red. And since we have those probability distributions, now we can say we want to generate some red points or blue points. We can sample at random from those probability distribution, generating red points by sampling from the distribution of the features in the red class, and the blue points by sampling from those in the blue class. So we get something that is similar to the kind of data that we used for training, because we are now sampling from the same probability distributions, at least from the ones that we estimated under the naive-Bayes assumption that the features are conditionally independent. Note that this assumption may not be true in all cases, so the quality of the results may vary from case to case. Okay, so now that we have several different classifiers, we can start thinking about the problem of deciding which one is best for each particular application. So suppose that we have this data set, the same data set, and we trained a logistic regression with polynomial expansions on the points, and we optimized the expansion. We trained a k nearest neighbor classifier. We also optimized k with cross-validation, and a naive-Bayes classifier with the kernel density estimation, also optimizing the kernel width so that we get the best results in each case. Now we have a test set of 45 points, and we see that with logistic regression on the test set we are making 10 errors, in k nearest neighbor 6, and in naive-Bayes only 1. So the question is, which of these is better? Can we say that a classifier is better than the other? The issue here is that we have this set of 45 points, and there is some randomness here. It could be that logistic regression had more errors than, for example, k nearest neighbors in these points, but this may not be significant because it can happen by chance. So the question is basically how likely it is that this can happen by chance, and how confident can we be that this is a significant difference. So one first approach is to assume that the number of errors that we are going to find in our test set is distributed around the true error multiplied by the size of the test set. So suppose that the true error of our hypothesis, of the final hypothesis, was 10%. This means that on average, for all the universe of points that we were to use, the error would be 10%. But we do not know this. We do not know what is the true probability of error because we cannot check for all the universe of points. However, we can assume that if we use 45 test points and we get, for example, 10 errors, these 10 errors are somewhere in the neighborhood of what we should expect with the 45 test points given the true error of our hypothesis. So if we assume that this is a normal distribution, then the mean would be the true error, the standard deviation would be also dependent on the true error, and so we can use our own measure of errors as estimates for this and obtain a confidence interval where we would expect to find the true error, or the true error multiplied by the size of the test set, so that this gives us the number of mistakes we are making on this test set, with a confidence of, for example, 95%. So if we assume normal distribution and we want a confidence of 95%, we have to go from minus 0.96 standard deviations to plus 1.96 standard deviation to plus 1.96 standard deviations. And this would be the interval where we could say with 95% confidence the true error rate should be found. So if we apply this to these results, we say that logistic regression should have, in this particular case, this hypothesis we obtained by logistic regression, should have a true error of around 10 plus minus 5.4 for any set of 45 examples. This would be the expected number of errors should fall somewhere in this interval, this for k-nearest neighbors and this for naive Bayes. So one thing that we can see here is that clearly naive Bayes and logistic regression must be different in their performance, because with this confidence, these intervals do not intersect. So we can say with 95% confidence that in this particular case, naive Bayes is better than the logistic regression we did there. But for example, between k-nearest neighbors and logistic regression, we cannot say that, because it can happen that the true error for these, both of these classifiers would be, for example, 8 in 45 points. So in that would be consistent with what we got here and what we got in k-nearest neighbors. So they could actually be equivalent, or even k-nearest neighbors could actually be worse than logistic regression, and this 10 and 6 was just by chance. So in this case, we would not be confident in separating these two. Another better test is this McNemar's test for paired data. The idea here is that we are using the same examples in the test set in the logistic regression, k-nearest neighbors, and so on. So since they are the same examples, and sometimes they are wrong and sometimes they are correctly classified, it's a good idea to check if the same example is wrong in one classifier but correct in the other. So McNemar's test uses this distribution here, which is, this is the number of examples that are wrong in classifier 1 but correct in classifier 2. This is the other way around. They are correct in classifier 1 and wrong in classifier 2. And we do the absolute value of the difference between them, minus 1 and then squared, and the sum of these. So this can be demonstrated to be distributed. If this is happening only by chance, so you have equivalent classifiers, but it happens that by chance some of them got this one wrong and that one right, and vice versa, then this would be distributed with a chi-square distribution with one degree of freedom. So basically, for 95% confidence, this value should be below 3.84 if it's just by chance. If it's above 3.84, then we can consider that the classifiers are actually different. They are not equivalent. So if we look at the logistic regression versus k-nearest neighbors, we do not have a significant difference. K-nearest neighbors versus naive Bayes, in this particular example, it was not significant. But when we compare these two hypotheses here, so this one obtained with logistic regression and this with naive Bayes for this particular data set, we see that in the the different results we got in the test set make this very significant. So this is unlikely to have occurred by chance, and we can say in this case that logistic regression and naive Bayes are performing differently with statistical significance. So since naive Bayes is actually also giving us a better result than logistic regression, we can say with confidence that not only are they classifying the examples differently, but actually naive Bayes is likely to be better than logistic regression in this particular case. Note, of course, that this is not a general statement about these classifiers, because it will depend on the data, on how we do the expansion for logistic regression and so forth. Okay, so one thing that we've been skipping a bit so far, and we just talked about standardization, normalization, and so on, is pre-processing our data. So basically rescaling the features, because depending on whether we are doing classification or regression, we may need to rescale the target values to avoid numerical problems. So usually in regression, we want to do our predictions to something that has a reasonable scale, around 0, plus or minus 1, something like that, because this makes it much easier to compute, to optimize parameters such as regularization, since those values, the target values, will influence the coefficients we have. It will usually avoid some numerical instability problems and so forth. Also, we can have features at different scales, so we may need to rescale them in order to make sense to bring them all together. So one thing that we need to consider when we are doing supervised learning is that we are trying to train on some data in order to predict something about new examples. So one question here is, how should we do rescaling? That initial, for example, standardization, where we subtract the mean and divide by the standard deviation. We have been doing this so far for the complete data set, because that is often the most convenient approach. We take all the data, we divide by the mean of each feature, we subtract the mean of each feature, divide by the standard deviation, and we have everything standardized. But in fact, if we do this, we are computing these scale parameters for the whole data, including the training set, the validation set, and things like that. And this may not be correct. So in theory, whenever we are computing something from the data, we should compute always on the training set and then apply that to validation or test set, because that way we can account for the error we get when we use the training set to compute the parameters and then apply generalized from there. Now, in the case of standardization, statistics like the mean and standard deviation converge very rapidly when we have a large sample of points taken from the same distribution. So in practice, it's often not worth the bother of doing standardization for example, for the different training sets used in cross-validation, and then doing it on the whole training set and applying to test set and so on. It's often a lot simpler to just do it once and then split the sets and do the rest of the computation. And in practice, this can make very little difference, because these scaling factors like the mean and standard deviation converge very rapidly if we are taking the points from the same distribution. So for example, suppose that we have 2,000 points taken from this distribution, and we are going to split them at random into 1,000 for training and 1,000 for test, for example. If we compute the mean for training and then apply to the test, the difference between the mean of 1,000 random points and another set of 1,000 random points is very small. It's about 1% of the standard deviation. So it's most likely that it's not worth the additional bother of doing this only for the training set and then applying for the test set, because the contribution of uncertainty about our true error that we're going to have because of this leakage of information from training to the test set, in this case, it's going to be irrelevant. So in cases like this, it's not worth trying to standardize each training fold during cross-validation and things like that, especially if you have a very large data set. And this would require, for example, pre-processing all the data over and over again during cross-validation, or storing different copies of the data rescaled at different scales and so on. This could be an overhead that is not justified in this case. However, this is not something that will always be like this. It may be more complicated if you are not sure the points come from the same distribution. For example, suppose that these 2,000 values we have are the money people are spending on transportation. And so some people spend lots of money on transport to go to work and so on. Others just walk and don't spend any money. And we have this distribution. And suppose this data come from different cities. In different cities, there are different levels of costs for transportation. So different cities may have different distributions. And the question is, do we compute the scaling parameters first, or do we need to compute them at each time we are doing cross-validation or something like that? And how do we split the data? And the question here depends on what you're trying to answer. Suppose we are taking examples from all the cities, and we want our hypothesis. We have a model that we want to train and find a way to predict something about the price of transportation for any of the same cities at random. So any person that can come from any city. Now we can just shuffle the data and rescale everything once, because we can assume that everything is basically coming from this distribution. Some points come from one city and others from another, but we are not making a distinction between cities, so it's like they come all from the overall distribution here in blue. And if we have a large number of points, the difference between the means and standard deviation of subsets of these points will be so small we can just ignore it. So we can shuffle this, do rescaling once. If we want to do cross-validation, it's probably a good idea to stratify so that the proportion of data from each city is the same in all of these sets, because if we change the proportions of the cities, we can change the distributions, and that can be a mistake if we assume that our future points can also come from any city with the same probabilities. So this would be the approach here. We don't care about the city, we just make sure that we have the same balance of cities, because that will be the expected distribution for the future data. And we can, in this case, if the data set is large enough, just rescale everything once, because it will not have a practical effect on the results. But now suppose that we are looking at different cities, and we are using examples from a set of cities, and we want to predict what will happen in other cities. So what we want our hypothesis to do is to give us predictions also about cities that are outside our training data. In that case, we must take into account that in different cities there are different distributions, and we cannot just assume that the means and standard deviations will always be the same. So in this case, we need to rescale for the training data only, and then see how this works with different cities. And we should also split our data when we consider training, validation, test, or cross-validation. We should make sure that different cities fall into different, or the points that come from the same city do not fall into different subsets. For example, we should not have points on the test set that come from the same city we have on the training set, because if we mix the cities that way, we are not simulating the real scenario where we will try to apply our hypothesis to predict something about different cities, because we will have the same points from the same cities mixed together. So in this particular case, you must be careful to make sure that you don't have in the training set points that come from cities in the test set, and also you should probably do rescaling only on the training set, and then see how that works out in the test set, because you cannot assume the distributions are the same. So we are not going to look into this in great detail, because as you can understand, this will depend a lot on the actual questions that you're asking, on the actual problem that you have. Sometimes you need to stratify your samples according to some attributes, which may not be the target class. There may be other things there that you need to ensure you have the correct distribution. The way you split training, validation, and test, or for cross-validation and testing, depends on how you on the actual questions and how you get the data and so on. So the important thing here is not to try to memorize these things as recipes. First we do this and then this and so forth, because this may lead you in the wrong direction in some particular cases. The important thing is to really understand these basic ideas of adjusting all your parameters for some data, which we call the training set, and then checking to see if this generalizes outside the data. Sometimes we can make assumptions that simplify things. Other times we need to check everything. So the main focus here would be to understand these basic notions so that you can think about what you're doing in each particular situation. Okay, so to summarize this part, we saw the ideal Bayes classifier, which is theoretically ideal, but in practice we cannot use it. And then we saw this simplification, naive Bayes classifier, which assumes conditional independence given the class. This is an assumption that may not hold in the data, but we are assuming it to make it easier to compute things, and allows us to use this classifier in practice. So in practice it tends to work rather well, and we can use it. That's also an advantage. So this we saw a bit this difference between parametric and non-parametric models. So basically, if you have everything specified by the parameters you compute and you can throw away the data and everything else, then you have a parametric model. If you don't have everything specified by the parameters and you still need the training data, that would be a non-parametric model. In the case of naive Bayes classifier, you can estimate the probability distribution in some parametric way, for example, computing frequencies or with a parametric distribution of probabilities, or you can use non-parametric models like kernel density estimation. So it depends on what you choose here. Naive Bayes and Bayes classifier are generative classifiers, because since we are estimating the joint probability distribution, we can either go from the features to the class or from the class to the features and generate new points. Classifiers like logistic regression are discriminative because they only give us conditional probabilities of the class given the features. So if we know the feature, we can estimate the probability of the class. But if we know the class, we don't know anything about what the features should be, so we cannot generate points with that information. We also saw a bit about comparing different classifiers to get an idea of whether or not they are different in a statistically significant way, and also processing data. So now that you already covered this part of training, validation, test, cross-validation, and so on, this is an important issue, and you should be very careful with this in practical applications, but it's something that is very dependent on what the actual problem is, and you really need to think about it when you're dealing with real data. The problems of stratification, of rescaling and things like that, you need to consider the actual problem you're trying to solve and think about the fundamentals and not just follow some generic recipe. So here are some sections from the textbook. You can read more on this.